Hello. In this video, what we're going to do is take a look at using a student's t-test to analyze two sets of data using Google Sheets. Okay, so for this example, I've opened up Google Sheets. I've opened up a data file with results from our salivary cortisol lab from Human Physiology in fall 2022. So we've got students 1 through 15 that provided saliva samples in the morning, so the AM column here, or in the evening, and the PM sample over here. The saliva samples were run through an ELISA for cortisol levels, and that's the results that are represented here. And so we've got student 1, sample in the morning, sample at night. We've already calculated the average and the standard deviation, so we have descriptive statistics to work about. But what we're interested in is trying to determine, is there a difference between the salivary cortisol levels in the AM versus the PM? So what we need to do is run a student's t-test to look for that difference. And so the way we're going to do this is we're going to use an extension within Google Sheets. And so click it up here. In this case, I've already got it installed, but I'm going to show you how to add it in. You go to the add-ons, get manage add-ons, get add-ons. And what you're going to want to do is look for XL-Miner. And so the XL-Miner Analysis Tool Pack. And in this case, it will give you the option, if you click on it, it will ask you if you want to install it. In my case, I've already installed it. Okay, once you have XL-Miner installed, you're basically going to go up here into the extensions on Google Sheets, pull that down, and then we can see that we've already added that in right now. So XL-Miner Analysis Tool Pack, we're going to click on Start. And this is going to pull up a window over here with all of the statistical tests that can be run. I want to run a t-test, so I'm going to pull down here. And at this point, we've got a couple options to work with. We've got a t-test paired to sample means, a t-test to sample assuming equal variances, and a t-test to sample assuming unequal variances. And so what we need to do is determine, are we going to be doing a paired versus two sample or independent t-test? And so we're going to take a short break and take a look at that. So basically, in any statistical test, you have the option to check between a one-tailed test and a two-tailed test. And so this is what is illustrated on the slide here. We've got our expected mean here based on our hypothesis, and we're looking at results that are either overestimated or underestimated. With a two-tailed test, we are looking at whether or not there is going to be a difference between the two groups of data that we're studying, but we're not saying that there's going to be a direction to that difference. And so we're looking at saying, is there a difference either at that kind of overestimated, that high end of the range, or is there a difference at that underestimated low end of the range? So we're not looking at whether or not this effect is going to be causing an increase or a decrease. We're looking at whether or not there is going to be a difference. The two-tailed tests are always going to be more conservative than a one-tailed test. So if you're at all uncertain, it's always appropriate to do a two-tailed test if you do not have evidence that there is a direction effect in your experiment. Now, the alternative to a two-tailed test is a one-tailed test. Again, this is used to determine if there is a difference between the two groups being studied, but there is an assumption of a direction effect. Now, when I say assumption, it means that you have prior knowledge indicating that there would be a direction effect. And so if you're looking at the effects of fertilizer on the growth of a plant, you would expect that the fertilizer is going to promote growth, and you would have evidence then, prior knowledge, that there is likely to be a direction effect. With this, we can then look at one end of the curve. We can look at a one-tailed test, and this is going to give us more power and more precision because we're only looking at one side of the null hypothesis expected results and looking at whether or not there is this direction effect. Now, please keep in mind that if you are not confident that there is going to be a direction effect, if you do a one-tailed test, you increase the likelihood that you are not going to accurately analyze your results. Okay, so based on what we talked about with the one-tailed versus two-tailed test, there is good evidence that the salivary cortisol levels are going to be higher in the day than they are at night. And so we could say that we are going to be doing a one-tailed test, but I'm going to assume that we don't necessarily have that information. And so I'm going to put a conservative two-tailed test in there. So I just enter 2 into that box, and again, it updates our formula there, and then it gives us the final argument within this calculation down here, type. It says type. Type is the kind of t-test, paired equals 1, 2 sample equal variance equals 2, or 2 sample unequal variance equals 3. And so this is, again, something that we need to determine prior to running our t-test for our experimental results. So to understand whether or not we're going to use a paired or an unpaired t-test, what we're looking at is a paired t-test is that there is some type of natural pairing in the results being analyzed. And so the example we've got here is basically the same subject with a sample in the morning and the same sample in the afternoon. And so we're basically testing the same group and the same subjects twice. And so in this case, the example up here on the slide is a pre-test, intervention, and a post-test. This would be an example of a paired t-test. We're looking at, again, the same group at different times like we're doing within this experiment. And so the pre-test, post-test situation is going to be a good example of a paired t-test. Now, we need to understand what are the other types of t-tests as well. Now, the two-sample t-tests are this idea that you're going to have a population, or at least a sample of the population that you're going to be looking at, and you're going to randomly associate or randomly assign those individuals either into one group or another group. A two-sample t-test is also referred to as an independent two-sample test. So in this case, we've got 2 examples. We've got 6 subjects that are available for our study. We are going to randomly assign 3 of those subjects into a group that receives a treatment. So they basically receive the intervention. And we are going to assign, again, randomly 3 of those subjects into a group that does not receive the intervention. And so this is, in essence, a control group. And so an example of this would be, we've got 6 plants. We are going to take 3 of those plants and provide them with the intervention, provide them with the treatment, so provide them with fertilizer, and then we would have another 3 plants that are down here that are receiving water alone. And so that's an example of a 2-sample t-test. Another example of that would be taking a look at the average height of male students compared to the average height of female students. And again, there are going to be different individuals, different subjects in the 2 different groups. Okay, so we've determined that in this set of data, it's going to be appropriate to use a paired test, but for completeness sake, I want to talk a little bit about the difference between equal variances and unequal variances. And so for that, we're going to return to the PowerPoint and look at the difference between equal variances and unequal variances. So with the equal variance, the idea is that we have basically the same amount of variation in the observations between the intervention group and the control group. And so when the variance is known to be equal, we can do a 2-sample equal variance test. Now, the way that we determine that is basically more math. And so if you are not sure if there is going to be equal variance, what you need to do is run an unequal variance test. And so an unequal variance test, a two-sample unequal variance test, is basically looking at the fact that in some situations we would have greater variability in our observations versus another group which has less variance or less variability. Now, the slide I've got up here is looking at the amount of time it takes to do a 1 mile run. Athletes that are conditioned are probably going to be running in a much less variation in their times, where non-athletes with variable levels of endurance and training and basically preparedness to run a mile is going to have a much greater variance. And so you're going to run a two-sample unequal variance test if the variances are not same, or if you're not sure if the variances are going to be the same or not. Okay, so based on that explanation, we know that what we're going to be doing is a paired two-sample t-test, two-sample for means. And so we're going to click on this t-test paired two-sample for means. And it's going to ask us for, what is the data that we are going to be analyzing. And so what we're going to do is we're going to go over here, and in this case we're going to start here with cell B1, hold the left mouse button down and highlight all of our values. And we're actually going to grab our header row here because we've got labels, so I can click the labels button right here. And so we've highlighted column A within our AM samples, which is going to be our variable 1 range. We left click on that box and it's going to update this. So this is B1 to B12. Then we need to select the second set of data because we're going to be comparing one set of data to the other set of data. Do the same basic thing. Hold the left mouse button down, highlight both the header and all of the data points. Then go over and click on our variable range here. We're going to click on that. This brought up C1 to C12. The alpha is going to be 0.05. That means we're going to be looking at a statistical value of less than 0.05 or less than or equal to 0.05. And then it's going to ask for a range. I don't want to overwrite my data, and so I'm going to click over here onto F1, click on this, and this is going to put our results starting within this cell right here. If you're not careful, you could possibly overwrite your data. We click on OK. It is going to run the statistics, and this gives us, again, some variables that we've already calculated. And so the means right here, the mean for the AM sample was 20.37. We've abbreviated that, or rounded that off to 20.4. Our PM sample, 14.86. We rounded off to 14.9. And then we got down here telling us both our degrees freedom, the statistics, our t-value, our test statistic value, and then we've got our two-tailed p-value here, p equal to 0.04. And then if you're interested, if you're using the old way of doing it with distribution tables, the t critical value for this set of data would be 2.228. Our t statistic value is greater than that, indicating that we have a significant difference between the groups. So what we're going to focus in on then is this p-value right here, 0.004. This is great, but what does it mean? So in order to understand what that p-value means, we need to review very quickly the difference between the acceptance region and the rejection region. And so the acceptance region, we're basically looking at whether or not our observed results are similar enough to our expected results based on our null hypothesis that we are going to be accepting our results as being due to chance alone. And so basically this acceptance region is going to be taking a look at our mean based on our hypothesis generated expected results, and we're going to be going plus and minus 1.96 standard deviations of that null mean. Now, the 1.96 standard deviations basically means that we're going to be looking at 95% of the observations that could be occurring in relationship to this mean. And so we're looking at this central point, and then basically half of 95% above that mean, half of 95% below that mean. And we're going to say basically that if our statistics are showing us a result within that area, it is going to be considered likely if our null hypothesis is true, and this is going to correspond to a p-value greater than 0.05. Now, the rejection region is basically the region underneath these tails, on the extreme region, kind of away from the mean based on our expected results. Now, the rejection region is going to be looking at those observations that are so extreme that they're greater than that 1.96 standard deviations away from that null hypothesis, meaning that these are values of our results, the test statistic, our t-value, in the case of what we're doing here, are going to be considered unlikely if our null hypothesis is true. And then in this case, we're going to have p less than or equal to 0.05, meaning that our results are going to be so extreme or so unlikely to occur, they're going to occur less than 5% of the time, less than 1 time out of 20, if our null hypothesis is true. So when we use this information for decision making, we basically have two situations. If our p-value is greater than 0.05, this p-value is telling us the probability that our observed results will occur if the null hypothesis is true. So if our p is greater than 0.05, it means that our observed results will be in the area underneath this curve, the area of these possible results, that could be true if our null hypothesis is true 95% of the time. What we're going to say then is that any variation we see in our observations in relationship to the expectations are likely to be caused due to random chance alone. And so with a p-value greater than 0.05, we're going to accept the null hypothesis, and basically accepting the null hypothesis means that there is no difference between the group and that the independent variable has no effect. Now, the alternative to the p-value being greater than 0.05 is a p-value that is less than or equal to 0.05. Again, the p-value is going to be indicating the probability that our observed results will occur if our null hypothesis is true. If our p-value is less than or equal to 0.05, this means that the observed results will be in this region, this 5% of the region. If we're doing a two-tailed test, the 5% of the region, 5 divided by 2, so the 2.5% of extreme results at the low end, and the 5% divided by 2, the 2.5% of the results at the extreme upper region. And again, remember, we're looking at p less than or equal to 0.05. We're looking at dividing that in 2, basically because we're looking at those extreme results at the high end and the low end in this example when we are using a two-tailed test. Again, this means that the observed results will be in this area, in the area in red, less than 5% of the time if that null hypothesis is true. And so if our results are falling at this extreme region, then the variation of the results is unlikely to be due to random chance alone. And so with a p-value less than 0.05, we are going to reject the null hypothesis. And if we reject the null hypothesis, that means we are going to accept our alternate or research hypothesis. The overall effect of this is that there will be a difference between the groups, and the independent variable has an effect. So when we put all of this information together with our sample example right here, we've got our AM sample with a mean of 20.4 plus or minus 2.6 nanograms per mil. Our PM sample had a mean of 14.9 plus or minus 5.2 nanograms per mil. We had a p-value based on our two-tailed paired t-test of 0.04, and we can summarize that as saying we have a p-value less than or equal to 0.01, 0.05, or in this case 0.01, a little bit more significant difference between the groups. In terms of decision making, we're looking at a p-value less than 0.01. That means that there is less than 1% of a chance that the results we're observing in this experiment are due to random chance alone if that null hypothesis is true. That means that we are going to reject our null hypothesis, and in the act of rejecting our null hypothesis, we are going to be accepting our research hypothesis. So to apply or use this decision in describing our results in a paper or a poster or a presentation, what we're going to do is use our means. So the AM sample mean of 20.4 plus or minus 2.6 nanograms per mil. Our PM sample had a mean of 14.9 plus or minus 5.2 nanograms per mil. And using our t-test, we calculate our p-value as 0.004, which we can abbreviate and basically round off as being p less than or equal to 0.01. Now, we are going to describe the results in words, and so we can have a sentence that looks something like this. The AM salivary cortisol sample, in parentheses 20.4 plus or minus 2.6 nanograms per mil, close paren, was significantly higher. We can make that statement based on the fact that we ran the statistics. The statistics showed p less than 0.05, which means that there will be a difference between a group, and that difference is significantly or statistically significant. And so the AM cortisol levels were significantly higher than the PM salivary cortisol levels, open paren 14.9 plus or minus 5.2 nanograms per mil, and then we add the p-value in the sentence as well to provide the evidence that we ran the statistics, and the statistics show that there is a true statistically significant difference between the two things that we're comparing here. In this case, we're going to put p less than or equal to 0.01. And then close paren and close the sentence out. So hopefully this helps you with understanding both how to do a t-test in Microsoft Excel, as well as what that information means and how we can use that information in a written lab report or a poster or any description of your results. Thank you and have a great day.